drawing Lewis structures of a little bit more complex compounds. So here we have Xenon Difluoride. This is from your Lewis structure lab. And it's a little tricky to figure out why there's bonding happening. So if you look at where xenon is located, it's right here in group 8. Now we know these are our noble gases. And our noble gases have completely filled shells, which makes them very unreactive. And that's why when we're making ionic or covalent compounds, we're constantly trying to reach noble gas configuration. We want 8. There's a few exceptions. We know that we can have an odd number, less than 8 or more than 8, depending on which elements we're dealing with on the periodic table and how many orbitals they have. Now, xenon difluoride exists, and here is why. So, on the periodic table, you can see the noble gases, and you can see that xenon is pretty far down, just like radon and krypton, down the group. Now, with the heavier metals, every time you go down the group, you're adding a shell. So 1, 2, 3, 4, 5. So I have my xenon. I have my 1, 2, 3, 4. This is such a beautiful circle. 5, shells. So every time you add a shell, the electrons that are on the outer shells are shielded. They're protected by the electrons that are on the inner shells. For that reason, it makes it a little bit easier to grab the shells from the noble gases. So there's only a few noble gases that can react, and it's krypton, xenon, and radon are the most common ones. For the specific reason that when you go further down the group, because you're increasing in shells, since you have more shells on the inside, more onion layers, they're protecting the electrons from feeling the full force of the nucleus. So this electron here doesn't feel that whole positive charge because there's electrons on the other shells protecting it. So xenon difluoride is possible for that reason. So how would we draw that structure? So I have xenon with 2 fluorines around it. Now you would think that, okay, well, I know xenon has 8 electrons in its shell. 1, 2, 3, 4, 5, 6, 7, 8. Each fluorine has 7. Why would xenon go in the middle? Well, that's for the reason that there's 2 fluorines and 1 xenon. They have to surround the xenon molecule. Now, how are they going to bond? Well, I know that my fluorine has to bond at least once to the xenon and then to the other xenon, the other fluorine. So, taking one of the pairs to bond to one fluorine and then the other, you would get something like this. We know that this is 14 because it's 7 times 2, and then this is 8. 8 plus 14 is 22. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Now, this looks a little funky, but let's figure out what the shape of this is. 2, 4, 6, 8. Oh, what am I doing? 1, 2, 3, 4. 1, 2, 3, 4, 5. 5 electron groups. 1, 2, 2 bonding groups. 3 lone pairs. That is a linear structure with a 180 degree bond angle. So basically, the more proper way that the structure looks like is that there's, since we can't really see it 3-dimensionally, but there's that lone pair here and the lone pairs around it with the fluorine atoms. The repulsions of the 3 lone pairs left forces the bonds to form a linear structure. So the reason this is possible is because xenon is so far down the periodic table for the noble gases that it makes the ionization energy low enough to bond. But it can only bond with the most electronegative elements. The 3 most electronegative elements on the periodic table are nitrogen, oxygen, and fluorine. Fluorine is the absolute most. Since when you go further down the group for xenon, your shells increase. And as your shells increase, you have more shielding. So the electrons on that 5th shell are more protected than the electrons in the 4th, the 3rd, the 2nd, or the 1st. So because you have more shells, it lowers the ionization energy just slightly enough for a little bit of reaction. But that doesn't mean it's going to be an ionic compound with something or a full covalent bond. It can only have that low of an ionization energy to slightly react with one of the most electronegative elements. Why is it one of the most electronegative elements? Well, if xenon just has a slight enough ionization energy to bond with something, it's going to be attracted towards something that really, really wants an electron, and that would be the most electronegative elements. Let's do one more little weird one for practice. Alrighty, let's do Bromine Trifluoride. So how many total electrons do we have? 7 for bromine, and then 3 times 7 for fluoride, 21, plus 7, that's 28. Now, bromine and fluorine can both bond the same amount once, but fluorines, there's 3 of them, and bromine, there's only 1. Also, fluorine is in period 2, where bromine is in period 4. So, we know that fluorine cannot expand its octet because it's in period 2. Fluorine only has s and p orbitals. Bromine has s, p, and d orbitals, so it can have expanded octet. So it will go in the middle. So I have my bromine and then my 3 fluorines around. Now I'm going to assign all my valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right. Well, now how do I make my bonds? I'm going to have a bond right here. Now, I still have this lonely electron and this lonely electron, and they'll have to bond too. So they bond here and here because one of the lone pairs has to break in order to form with the fluorines. So then my structure will look like this. 2 lone pairs, and then 3 bonds. The reason that the bonds are formed is because since bromine is a compound with fluoride, the sharing of electrons does happen, and it happens with one of the lone pairs repelling each other into singular electrons and forming with both fluorines to make bonds. What kind of a shape does this have? 1, 2, 3, 4, 5. 5 electron groups, 3 bonding pairs, 2 lone pairs. That would be a T-shaped. And it has a less than 90-degree angle. Awesome. Now, how can I draw that as a 3-dimensional structure? A T-shaped has bromine, and then 3 of the bonds in planar view. And then the electron pairs are going out into the plane and out of the plane. What's one more that we could do? Let's do Bromine Tetrafluoride, BrF4-. So now I have 7 plus 4 times 7 plus 1 for that extra electron here. So that's 7 plus 28 plus 1, which is 36. So bromine, and then my 4 fluorines around, and then my 7 valence electrons. Now I have my extra electron, and where would I place it? Well, if I place it towards any of my fluorines are satisfied because they cannot expand the octet since they're in period 2, and they wouldn't bond with my bromine, and that's not possible because I know this is a molecule. Whoops. So I'm going to take this extra electron away. I know I can't place it to any of my fluorines, but I can place it to my bromine. Well, if I do this, then that looks super weird because now my bromine is satisfied. However, bromine can have an expanded octet. And I know that bromine has an s orbital, which can have 2 electrons, and then it can have The others in the p orbital, that's 8. It also has those 5 d orbitals. So therefore, these are where the bonds come into play. So then it can bond here and here with that fluorine, here and here with this fluorine, whoops, to give us 2 bonds and 2 lone pairs. And what shape is this? 1, 2, 3, 4, 5, 6 electron groups, 4 bonding pairs, and 2 lone pairs. That shape would be, I have to actually, square planar. So when you have 6 electron groups, 4 bonding groups, and 2 lone pairs, you have a octahedral electron geometry. And then what kind of molecular geometry do you have? I'm just looking at my table to double check my work because sometimes I mix some of them up. Let's see. Octahedral, we have square planar. Yay, I was right. So we have our octahedral for the electron geometry. And then we have the square planar when you have 2 bonds, 2 lone pairs and 4 bonds for the shape, the molecular geometry. So it looks like this. It's just planar, where you have the bromine, the 2 fluorines around it in planar sight, and then the electrons coming in and out of the plane.